draft science, physics particularly, draftphysics.com. Anyway, video. So we're slit stuff here still. So hopefully these images just aren't great, but they'll have to do. So we're talking about the single slit at the moment, and we'll get to the double slit, which we've got a good image of it here in different varieties. This is what the pattern in the ideal sense should look like. And what we're really going to be talking about, though, is what's happening here, because it's not what the math says should be happening, in the sense that there isn't a perfect sine wave gradation in intensity between the empty spaces and the bright spaces. And the only thing that's really creating any kind of gee, it just sucks getting old. Any kind of gradation in the intensity is actually this arc. The fact that they get shorter, and then they get bigger, and it's the shortness that's creating most of the appearance of diminishment or gradation. So theoretically, because of the way the experiment's done with laser beams, as I've pointed out in the previous video, the laser is on top of this opening, and this opening's usually, the slit is usually much taller than it is wide, of course, and that means that this portion of the laser beam will be relevant where this edge won't be. So this is the cut off part, and this is the part that remains of the actual image of the laser. And I would argue that that's what this arc represents, is the image of the laser. That where each photon went in is revealed in the pattern. It's still in there. So it's just basically this image stretched very large. Oh, great, 2 pieces of paper. I just wrote on some other piece of paper. Anyway, I'll do better. So you can sort of see this. So it's just this stretched. So the divergence of the laser beam, so laser beams diverge. So they start off here and they do get a little bit bigger. This is a huge exaggeration. But they diverge as they go out. So the size that increases this way of the image, so when the image gets bigger this way, that's just the divergence of the laser beam. And the spreading this way is the spreading being caused by the effect of this surface that's interrupting the beam. Alright, so I attempted to do the gradation thing, and it's, my drawing just can't do it with this pen. Anyway, but this is how it's supposed to look. It's supposed to have this appearance of bright, and then it gradually goes to dark, and then it gradually goes to bright, and it gradually goes to dark. And this clearly looks like none of that. This doesn't have any of that. It's just clearly almost a dot, a circle, a nothing, a circle, a nothing, a circle. So it's just almost like it's an image, no image, image, no image. And there's a space between the images. Alright, the other thing that's never done with this experiment is, I'll see if I can draw this so I can do both explanations. They always project it on a flat surface. And so you have this idea that there's some sort of infinite place you can go this way and this way, because this plane goes infinitely. Okay. But what's really happening by the numbers, that is, this distance appears to get wider and wider as you go out, but it's really not. It's really the same distance always between the little bright clumps. It's just that the fact is you're spreading it further out, which just you're magnifying, in a sense, the image by stretching it again. So to do this experiment correctly, to view it correctly, what the map should be acknowledging is that this is how it should be projected. It should be projected on the circle that has this radius. This distance should be the radius of the circle, and the image should be understood to be that image. So once you put the circle around the theater of this experiment, you sort of understand there's no such thing as an infinite place it could go. And it's really just going to create exactly the same size pattern. All these will be exactly the same spacing, same exact pattern. They'll just get less of it. So this will be brighter, this will be less bright, less bright, less bright, less bright, less bright. See, but by projecting it on a flat surface, you stretch it. All these get stretched, preposterously stretched, especially the empty space. So you have this illusion of a diminishing and weakening, and it's exaggerating the weakening of the pattern, and it's certainly exaggerating how it's just kind of fading off into the distance, because it really won't do that in the real world. So this sort of this is something they should have fixed a long time ago, in terms of recognizing that this is kind of an optical illusion. This isn't the correct way to view something, isn't on a flat screen, because it distorts it. I mean, they even did this with movies now, and they even have home TV screens that are arced, to compensate for the fact that you do break things by stretching them, by projecting them. You're stretching them. All right. Not a big point, but I'm just saying it's something that an experiment that's supposed to be a foundation for an entire conclusion, proof of wave theory, that you'd think they would have been more rigorous in this analysis and recognized these truths. Certainly this truth, not being any part of the reality, should be acknowledged. And this deception of optical distortion, and that's all it is. It's just an optical distortion that they should have already. We already should have software where you just punch in how far away this was from the target, and it automatically corrects the image. That kind of stuff should already exist, considering how important the experiment is. All right, so I will now explain, okay, what's really happening. I think I'm pretty confident now, getting more and more confident with each version. All right, so I have been speculating that these are all just images, and the fact that we have this illusion because of the flat surface that they're not equidistant, but they are equidistant. So there's exactly the same amount of angular, there's a proportional angular difference, double the angle. So you just double the angle, same image, same image, same image. So it's all the even angles will be on, the odd angles will be off, that kind of thing. So if I just made it arbitrarily 3 degrees, you could figure out that it'll be at 3, and it'll be at 6, and everything in between will be 5 or 4 or whatever will be blank. Well, I'll get to that more completely. Alright, so let's just draw the slit, and I think I can explain it from there. And so we'll just make a little bit bigger version of it. Alright, so this is your slit, and that's really kind of crappy. And so this is the part that's going to get affected. So we understand that this part of the arc, the two sides here of the arc, no photons go there. So that's why it's not rectangular, and that's why there's no representation for those elements. So the idea would be is that, see, it's probably a better way to draw this, so I'll do it this way instead. Alright, we won't worry about this side for this part of the argument, but this side's going to be affecting it also. So let's just say there's electrons in a field configuration. I mean, they have a certain order. They're arranged in a certain way. because they're charged. And so each photon is going to go into this field. Now you can understand that if the photon goes through the middle, well, there's probably, well, it doesn't matter. Alright, you can figure the middle, this is it's even if it hits an electron in the middle electron perpendicular. So we're going to really talk about what's perpendicular from this arc. That's the direction that the electron will knock the light, let's say. And let's say it always goes a certain degrees. So we'll just say it's 4 degrees for the sake of argument. When it hits an electron on this arc is a 4-degree arc. So anywhere on the arc is 4 degrees. 4 degrees. So anyway, 4 degrees off this perpendicular. Okay, so that's, obviously this isn't 4 degrees, but I'm just doing this for the sake of argument. So every time it hits an electron, it goes exactly the same 4 degrees. The same degrees. It's probably 40 degrees. So why don't we just say 40? There. We'll fix it. Alright, so it goes 40 degrees. This doesn't matter. Alright, anyway, so the first ones, you can see the middle ones would go through, and if they don't hit any electrons, so if this one goes through and it doesn't hit any, or if this one even goes through and it doesn't hit any, or this one goes through and it doesn't hit any, all of those will end up projected. Now this would be much larger on the screen, but it'll end up being just the divergence. So it'll just go the distance of this divergence. So let's say the image on the screen is 2 inches high. Okay, so we have a pattern on the screen, and let's just say it's 2 inches at its maximum high. And so this would be like 4 inches. This would be 2 inches high. That's what this will end up. So there'll be a certain number of photons that will just duplicate the laser beam exactly as it is. They won't hit any electrons. So each one of the photons will just go straight through, go right to the middle, and they'll just do the normal divergence, which will be the same distance this way as this way. They'll just duplicate the circle of the laser beam. Alright, now let's say this one comes through and it hits 1 electron. So this is, you understand this middle line. So this will be 40 degrees this way from this side, and this way from this side. So you can't change that. So a photon comes in, say this over this side. It can hit here, or it can hit here, it can hit here, or it cannot hit. So if it doesn't hit, it goes here. If it hit once, okay, so if it hits 1 electron on its path, that means it'll just be diverged that 140 degrees, or see, like I said, it's much less than 40, but anyway, for the sake of arguments, let's just use 4 or something. So anyway, it will get knocked and it'll end up here, and if it hits the electron when it goes right near this edge, then it'll end up just a little bit further over, but same idea. Just same 40 degrees, but just the distance in this gap. You can sort of get that. So that is what's, and so the other side would do the same thing. It would go this way, and the entire, for this half of the beam, would end up here and here. And so that creates your central maxima here, those degrees. Now if it hits 2 electrons, right, then that's going to be a total of 8 degrees. And so from this side, the 8 degrees, see, now I'm going to get myself into a little trouble. Oh yeah, that's why that's why you have to use this other side too. The other side is doing exactly the reverse. So that's the part I forgot to include. Yeah. So you have to the other side's going to end up, this side will end up going that way, the opposite way, because your perpendicular from the arc is opposite what it is when you go hitting the outside. So when you're hitting the outside going into the circle, you go the opposite way. When you hit the electron going the other way, you go the other way. So anyway, let's just, so it hits an electron here, and then it hits a second one. So it hit one and got knocked 4 degrees, and then it hit another electron, got hit another 4 degrees, and that's why it ends up over here. And so you'll have another duplicate of this scenario over here. and it's got the same arc of the laser is still there. And then so on. If it hits 3 electrons, it ends up over here, and if it hits 4, it ends up over here. That's why they get so much dimmer, is because the odds of hitting 4 or 5 or 10 electrons, the odds get higher and higher, and as you make the slit narrower and narrower. See, when the slits are pretty wide, there's lots of room for electrons. Lots of electrons can fit in here. But when you make the slits close together, then the problem becomes there's very little room for electrons, and as you go this way, like if you tried to bulge them going this way, well, then the problem becomes they lose their charge connection. There's no protons. They're too far away from the protons, so they can't go way up here. So they end up going this way. They start flowing back onto this surface. So that's where all the extra electrons go. So as you bring this thing closer and closer, the electrons start to flow back onto the surface of the material, and they're not bulging here anymore. They're not consolidating. So you have fewer and fewer electrons to hit, and that's why you end up with a very simple pattern, because very few electrons, very few photons can hit more than 2 or 3 electrons. That's all they can hit. And their spacing changes because the bulge has changed. The amount they have, the surface for which the surface for which they are, like I said, when it's a wide slit and a narrow slit, the ability for the electrons, the spacing of the electrons is changing. All right. So, so these are basically photon for photon kind of images. Now, the part where it does get a little messy is when this one gets diverged this way. So this was a photon from this side, and now it's going to go over to this side, this side, because it's switching sides. And so now it can hit the first electron on this side, and then it'll hit the second electron over on this side. And but that's going to end up filling this space because the angle will be slightly different than when you hit it here because of this distance difference. And yeah. So anyway, so these are just, so like I said, so if you you just do this 4-degree thing, 8 degrees, 12 degrees, 16 degrees. So you just think of it that way, and everything in between is the spread that doesn't fit. So the first one has essentially 2 images on either side of it. So it's got the middle one in here, and the rest of the image is made out of essentially these 2 superimposed. So it's got the circle in the middle, and then it's got this and this superimposed on it. And those are the 2 first 4-degreers. And then at like 6 degrees, there's nothing. And then at 8 degrees, you have another pattern. And then at 10 degrees, there's nothing. And at 12 degrees, you have another pattern. And then blah, 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 going onward. And they get weaker and weaker and weaker because fewer and fewer photons happen to hit that number of electrons. The odds of hitting 5 or 10 or 15 would be very low, where the odds of hitting 1 would be very high. So that's why 80% of the photons end up here. It's because 80% of them are just going to hit 1 or less. And then, 5% are going to hit, well, it comes out to 10%, close to it anyway. Let's say 8% for accuracy. So these are both going to be 4 point something. So a total of 8% will hit 2 electrons. And then you get down to like 3% will hit 3 electrons. And then you get down to like 1.5% will hit 4 electrons, that kind of thing. But it depends on how wide the slit is, obviously, how those percentages will start changing. So what else did I want to say? So yeah, so there should be a way to, I mean, I'm sure there's probably somebody who has done this, but I mean, you can't find it. But you should be able to just shape the laser beam going into the experiment, like just put a star in front of the laser or something. So I'll try to do that. I mean, I know you can buy cutouts that fit on lasers. I have to see if I can just buy that without, you know, I'm not going to pay $3. Yeah, just going to find some way to get it thrown in for free or something. Well, anyway, I mean, it's probably worth $3 just to do this. But anyway, you could, you know, just some kind of irregular pattern that you could see is being projected onto these little images, especially on when it comes to the top part of the laser. If you can mess up this part of the laser beam, the top part, then you should be able to see any distortion. So if you just had like little V's cut, you know, in the top and bottom of the laser beam, you should be able to duplicate that in the image, and that should. Oh yeah, the other thing to be clear on is that different color light will reflect by a different percentage. So, you know, that gets back to this image. So the green light or blue light would be even narrower, and the blue light would only deflect by, say, 3 degrees, and then the red would be, let's say, 5 degrees, and then the yellow would be in between. That kind of thing. And so that just changes where these patterns will locate. It's just because the different wavelength of light will alter, have its direction altered by a subtle different degrees each time it hits an electron. So yeah, so you can see this one's a little bit flatter, but you can also see that the slits must have been a little bit short, because you can see they were starting to get patterns going up. And the way you can get patterns going up is your slit has to have, your edge of your slit has to be almost as high as your laser. So it would have been a little more, the beam for the red laser was obviously, in my opinion, smaller than the beam for the green laser when these pictures, you know, was actually done. It would appear that way anyway, because there seems to be a lot less diffraction going this way from the red. The orange seems to have a lot. So I mean, I'm pretty sure these images were just superimposed. I would think they might have been taken at one time. Oh, that's probably it. It was taken at one time. All 3 were sent through a very long slit, and you know, it still doesn't explain all this orange down here, but it certainly would explain the green. The green got a little too close to the top slit, the end of the slit, and that's why it started diffracting up. But anyway, not really important. Bigger fish to fry. But you can certainly see in the diffracted image, you know, this image is being diffracted up here, and there's absolutely no gradation. I mean, these are just almost clear little circles. So, anyway. Yeah, but you can see it in here. You know, these couldn't be flatter. I mean, they're just kind of a flat, even intensity. There's absolutely no really bright in the middle, and then really dark in between, and no flow, no doesn't graduate. Oh, God. They say it sucks getting old. It doesn't proportionally as a parabola get weaker and stronger, brighter and dimmer. And it's important because the math says it should, and it doesn't. So again, they keep talking about how this is the most predictive math in the universe, how this is the most predictive theory, and it's always getting the right answer, and it's so great. And it really isn't very good when you really look at it, and no one cares to really look. For me, apparently. I have to do everything on this planet. Everything good that's going to get done on this planet, apparently I have to do it, because everybody else is a piece of suck. You know, except for Dr. Kevorkian. He was the only other good human being. It was him and me, and everybody else is suck. It's very depressing. Alright, anyway, I didn't do a brilliant job of this, but I think you get the drift of it. Stop this. I didn't want to watch the video.
Coney Island.
You're gonna play two ads? Two?
The beach, the boardwalk. I work here on base 7.
Fuck you, cunt. I love this song. Yeah. Very good. Really is brilliant. Even the lyrics are good. I hate lyrics, but I love the lyrics of this song. This girl is only gonna break your heart. A little settle line here. Alright, get to it already. It's just really nice. And you're a piece of suck, so I'm fucked. Really good. I never dreamed that I'd meet somebody like you. She'll ruin you. Yep, okay, enough of that. Yeah. Anyway. This is a happy accident in my opinion. But I don't know why it happened exactly. Still can't figure that out. I'm just switching tabs, you know. I must have hit something. So anyway, back to the serious physics. Enough of the bitches. Anyway, yeah, so I think I got a good argument here that the your Huygens thing ain't going to be able to get around all these arguments. It's crap. It's not what's happening. And yeah, this isn't any kind of wave thing. It's clearly just what Feynman would describe in a Feynman diagram. It's a photon hitting electrons, imposing a little bit of momentum, and then the electron readmits the photon at a different angle. It's really not any more complicated than that. It really isn't. I mean, I'll draw it. Okay, let's say there's a tension of the electron. So the electron's under some kind of tension. The photon hits it here, going this way. The electron moves this way because it has a tension. It's caught between other electrons. And when it moves back, because that's what it's going to do, it's going to say, screw this momentum, I want to go home because I don't like these assholes and they're getting too close to me and they're smelly. And I don't like the smell of them. And so it's going to say, I'm going back home. And to go back home, it has to fart out the photon this way. So it gets hit by the poo here, it moves a little bit, and then when it goes back home, it shoots some poo that way. You could think of it, this fall goes into the mouth of the electron, it gets startled, it spins around a little bit, and then it poos it out this way. I don't know why I have to use a poo metaphor, that just kind of spoils the video. Really. I mean, putting poo and shit in my own video, I mean, that was really stupid. But anyway, this is a function of the universe right here. Energy, a little bit of momentum. You lose the momentum, you have to you switch the momentum. You go back home, you have to get rid of the momentum. All Newtonian, all angular, no wavy mush needed. So anyway, I have to do this video better than I did this, so I will attempt to do that in the future. But I think this is getting close to the truth, the facts, the actual accurate description of reality.